one, give me 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 one.
Good morning. Today we will discuss another topic in computational fluid dynamics, very important topic. The forms of governing equations suited for CFD. Myself, I am P. Venkata Mahesh, Assistant Professor in Department of Mechanical Engineering, Institute of Aeronautical Engineering. Now, what is these forms of governing equations particularly suited for CFD means? As the name suggests, the CFD, the computational fluid dynamics, the entire process is based on coding. Okay, we have to apply the finite element method or finite volume method or finite difference method. Using this method, we have to write some code, CFD code. Okay, now while writing the code, the general way to do is we have to simplify the logic. Okay, the logic should be simplified. The program length should be small and it should be organized properly. So for this reason, we have to see that the governing equations are in a form which can be which can be used for simplifying and organizing the logic of the computer program. Okay. Now the conservation forms of equation that we have seen in the last few classes we have seen the conservation forms of governing equation. In that you will see the divergence term on the left hand side. Okay, the conservation form means there is a divergence term on the left hand side. The conservation forms of governing equation provides the numerical program the convenience. Okay, why we are taking the conservation form means it will give some convenience for writing the computer program, and the continuity equation, we have continuity equation, we have three momentum equations, we have energy equations. So all these five equations, if they are in the same form, okay, if they are all these things can be expressed in a same form, then it can the logic or the code that we develop can be easily organized. Okay, that is the reason we are doing this exercise. Now if you recollect, this is the continuity equation, these are the momentum equations, and this is the energy equation. Now here this is the divergence term I was talking about. You can see the divergence term is there in all the five equations. So because of this divergence term, these equations are classified as conservation form. And these equations, if you see, they are having a flux term. Okay, the mass flux, momentum flux, energy flux. Okay, mass flux, momentum flux, energy flux. These terms are there in this equation. You can see here, this is mass flux, this is x momentum flux, this is y momentum flux, and this is z momentum flux, and this is energy flux. So if you see any commercial code like CFX or Fluent, what they will do, they will give the values or the errors in evaluating these terms. Okay, these flux terms they will evaluate, and they will see that the error in calculating these terms is minimum, and that is given in the form of a graph like this. Okay, and in this graph it shows by step how the error in calculating these terms is going to be there actually. How it is, in what fashion the error is happening, progressing. Whether it is converging means it is reducing, or whether it is increasing. Increasing means diverging. So this is the primary interest for us while solving the governing equations using CFD program. Now, where we came across while using this approach, the control volume approach, which is fixed in one place and the fluid is moving across. In this case, while deriving what we have used is, we have directly taken the flux terms into the account. Okay. In this equation, in this approach only, we used directly the flux terms. So here these flux terms are called the dependent variables, and the pressure, density, velocity, these are called the primitive variables. Okay, these are the main dependent variables. The flux terms are called main or important dependent variables, and from these we'll calculate what is the primitive variables. Now if I expand the left hand side divergence term, how these governing equations look like? These governing equations will be looking like this. So this del dot rho v bar is there. Del dot rho v bar is there in the previous slide. That del dot rho v bar is expanded like this in partial differentiation form. Why we have done this, I will see in a few seconds. Now in the same way, we have del dot rho u v bar. Okay, del dot rho u v bar, and we have rho v bar, we have rho w v bar. So all these terms are there in this momentum equation. These terms are expanded here. Okay. Similarly, we have expanded the energy term also. Energy flux also we have expanded. Why we have to expand this? That is the important question here. Here if you see on the right hand side, you can see the partial differentiation terms. Now if I expand this divergence into another xyz terms, what I can do? I can club these partial differential terms in one form. Now here in this particular case, the right hand side xyz partial differentiations are there appearing separately, and in left hand side xyz are there separately. So this kind of form is called weak conservation form. Okay, these are called weak conservation forms. Okay, they are conservation forms, but they are weak conservation forms. How to make it a strong or effective conservation form? That we are going to see. Now, if all these equations can be expressed in one particular form, that is called the generic form of governing equation. So the generic form of governing equation looks like this, and here U, F, G, H, J, they are all vectors, column vectors. And if I express all these equations in this form, then it is called the strong conservation form. Okay. Now, what is this U, F, G, H, J represents? That we will see in the next slide. Now here we will see the first term U. What is U here? So how to get U? Here dou U by dou T is there. So in these equations, if I arrange all the partial differentiation with respect to time, so this is the one, this is the second term, third term, fourth term, and this is the fifth term. Here anything is there? No other terms on the right hand side. So we have only 5 terms. If I arrange these 5 terms in a column vector, then that is defined as U, like this. Okay, U is equal to rho U, rho V, rho W, rho into E plus V by 2, V square by 2. So this is the column vector U. Similarly, I can write F, G, H, J. We will see it in the next slide. Now coming to F. Okay, what is F? F is partial differentiation with respect to X. So here on left hand side I have partial differentiation with respect to X. There is no term on the right hand side. So here it is on left hand side. So it is a positive one. So if I bring this one and this one this side, so this will become positive and this will become negative. Similarly, I have another term here. If I bring this term this side, what will happen? This will become a negative here. Now here this is another term, x term on the left side. Here I have an x term, partial differentiation with respect to x term on the right side, and similarly I have a partial differentiation term, x term on the left hand side, and here we will see how many terms are there. This is one term, partial differentiation with x. This is another term, partial differentiation with x. This is another term, partial differentiation with x. And this is another term, partial differentiation with x. So many terms are there. And this is another term, partial differentiation with respect to x. Now, if I bring here u is the f is on the left hand side. So I have to bring all the right hand side terms onto the left hand side, and then I can arrange these terms in form of a column vector. So if I write all these things, it will look like this. So rho u here, rho u square minus p, it will come here and it will become plus, and here plus tau xx is there, it comes this side and becomes minus tau xx. So like this, rho uv minus tau xy, rho wu and minus tau xz, and rho into v plus v square by 2 into u plus pu. So this pu is there here. Where is the pu? Yeah, this pu, it comes this side and becomes plus. And here it is a plus k dou by dou x. It will become minus here, and here minus u tau xx minus v tau xy minus w tau xz. So this is the term f. Okay. Similarly, we can write it for the g. So how to write it for g? So g is the partial differentiation with respect to y. So here I have a partial differentiation with respect to y term. Here I have a partial differentiation with respect to y term. Here I have a partial differentiation with respect to y term. And here this is another term. This is another term. This is another term. Like that we have many terms here. So this is the another partial differentiation with respect to y. This is another partial differentiation with respect to y. This is another partial differentiation with respect to y. This is another partial differentiation with respect to y. This is another partial differentiation with respect to y. This is another partial differentiation with respect to y. Now again, similar way, what we have done for f, we have to bring all the right hand side terms involving the partial differentiation with respect to y on the left hand side and write the column vector for g. Okay. So what will be there in g? I will have rho v, rho uv minus tau yx and rho v square minus tau yy plus p and rho vw minus tau yz and p e plus v square by 2 into v plus pv minus k into dou t by dou y minus u yx minus u y tau yx and minus v tau yy minus w tau yz. All these terms will be there in E. What is this? This is G. Okay. So in this way you can write the G vector. Now coming to the H vector. How to write H vector? H vector is having partial differentiation with respect to Z. So partial differentiation with respect to Z means this is one term, this is another term, this is another term, this is another term, this is another term, here one term, here one term, this is another term, this is another term, here one Z term is there, here one Z term is there, here one Z term is there, and here one Z term is there. So if I bring all the Z terms on the right hand side to the left hand side, and if I assemble all these things, I can write a column vector in the name of H. So this column vector looks like this. Okay. So what is this? It is rho W from the continuity equation. Rho UV minus tau ZX. It is from momentum equation. Rho VW minus tau ZX. So ZY. This is from momentum equation. And here rho V square plus V plus P minus tau ZZ. This is from momentum equation. And similarly, this is the from energy equation. Now, this is the vector H. So the vector H is represented by all these terms, column vector. Okay. Coming to J. So what is this J? It is all these terms without any differentiation. Okay. So the J is not having any partial differentiation. So all the terms which are not having any partial differentiation, they are on the right hand side. We will make them as one column vector. So here how many terms are there? This is one term, this is another term, and this is one term, two term, three term, and here in continuity equation there is no term. So if I write all these in the form of a vector, it will be like this. Okay. Now rho into UFX plus VFY plus WFZ. What is this? It is the expansion of this F dot V bar. F bar dot V bar. So what is F? F is Fx I Fi J plus Fwk. And what is V bar? Ui plus Vj plus Wk. If I make a dot product of this, I will get this one. So this term is giving us the J. So this is the generic form of governing equation. And if I write all these things in this term, what I can do, I can simply write the code for this and I can use all these column vectors. So it will make the code very simple and organized. Now in these equations, the F, G, H, they are called the flux vectors because they are containing the flux terms. And J is the source term. So J is the source term means what? If the body forces are absent and there is no volumetric heating, then this will become 0. Okay. If the body forces are not present in the fluid and if there is no volumetric heating because of radiation, then this term J will become 0. So that will become simplified. Now the column vector U is the solution vector. Now this here, if I solve this equation, I will get all the values of the flux variables. Okay, if I solve this equation, I will get the values in the form of flux variables. And these flux variables appear in F, G, H as I already mentioned. Now from these flux variables, I can find out the values of the primitive variables rho, U, V, W, P and E in this fashion. So here rho is directly I can take because I don't have to calculate rho. And if I find out what is U, how to find out? I have momentum. From momentum, if I divide with rho, I will get U. V, if I divide the V momentum, I will get V. If I the W flux, momentum flux, if I divide with rho, I will get W. And this is the energy flux minus the kinetic energy. The energy flux minus kinetic energy, because already I have divided, I have find out what is UVW. If I eliminate these things, I can find out what is the internal energy. Okay. So this is the way I have to find out the primitive variables. Now, in some cases, the flow is inviscid. So what do you mean by inviscid? The viscous forces are negligible. So if the viscous forces are negligible, what is going to happen for this generic equation? What is going to happen to this volume, the vectors, okay? The column vectors. What is going to happen to this column vectors? Here, is there any viscous term for u? If you consider u, there is no viscous term, so nothing is going to happen u, it is going to remain same. Now if I take the f term, f is having, this is a viscous term, this is based on viscosity, this is based on viscosity, this is based on viscosity, this one and this one. So all these viscosity terms will vanish and I will get a simplified term like this. Okay, so this is the inviscid flow equation. Okay, inviscid flow equation, wherein the, what is this? The conduction is also negligible. In the flow is inviscid, then the conduction is also negligible in fluids. Now if I come to the term G, so here I have, this is one viscous term, this is another viscous term, this is another viscous term, these are three viscous terms here, and again because inviscid, the conduction is also negligible, so I can eliminate this, and if I eliminate all these terms, the column vector is going to become like this. Okay, so this is for inviscid flow. Similarly, I can write for H, here also I can remove this one, this one, this one, all these are viscous terms, all these viscous terms are removed, and since viscosity is not there, there is no conduction in the fluids, then from, if I simplify this, I will get this equation. So this is the column vector for inviscid flow. Similarly, if I come to J, so the J term is this, that is we have already derived, and in this if you see there is no viscous term, so the J is going to remain same. Now if the flow is a steady invisible flow, okay, steady fluid and inviscid fluid, then what is happening? Steady means the term dou u by dou t is becoming 0. If I eliminate this, what happens to the equation? So it becomes further simplified. Dou f by dou x equal to j minus this. Okay, this I can write this or in this way. Sometimes I will write in this manner also. So this is about steady inviscid fluid. Now what we have done in this class, we have listed out all the governing equations in conservation form, and we found out that on the right hand side there are x, y, z terms separately. So what we did, we have expanded the divergence term and we took all these x, y, z terms onto the left hand side and we clubbed them into one form, and then we made the generic equation in the form of dou u by dou t plus dou f by dou x, dou g by dou y plus dou h by dou z equal to j. And we have from that equation we have found out what is this u representing, what is this f representing, what is this g representing, h representing and j representing, and how these equations transform in the case of an inviscid flow and in the case of a steady flow. So this is what we have seen today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.